gets me every time. This concludes our test of the emergency broadcast system. You may now resume your lives. Good. Microphone is on. Good, good, good. Bow tie is present and accounted for. Hello! Hello, everyone. Welcome to yet another edition of this darn class that you have to take. So as some of you have been observing in the chat, there have been some rather major restructurings that I was hinting at before. We've come to a conclusion about what we want those restructurings to look like for this particular offering of this particular course. So, just to recap the problem, we had designed this course in with the idea that we would be able to do auto grading in mind. If we actually if we don't have the auto grading available, we don't have as many resources available to do grading, which means that we can't do as many evaluations, and that the evaluations we do will not be able to get them back to you in the same time frame. So there's been some change to answer that question. So to clarify, the actual dates for the tests will be October 24th and November 26th or 28th. Let's see. October 25th, October 24th to 25th, November 28th to 29th, October. Test 1 should be occurring at the end of week 7. The end of week 7 is the 24th. So yes, that's correct. And test 2 should occur in week 12, which is one day less than the 29th, which is the 28th. So yes, those are the correct dates now. Yes. Yes. Sorry about that. So basically, in order... Oh. Does that conflict with another midterm that you guys have? Yeah, okay. So as I have just demonstrated, these dates are a little bit, things are in flux to a certain degree. So if there are any big midterms in or around those dates, please let me know, and we'll see if we can't shift things around a little bit. Okay, what is 2PO4 as well? And is that a mechatronics course? Or like something. I don't know. What course is that, basically? So anyway, there are a few adjustments that have been made. We've gone from 3 midterms to 2. We've gone from 10 assignments to 6 assignments. Furthermore, the weightings of the various categories have been adjusted. Assignments are still worth 20, but 5% that was in tests is now in the exam. That's just, rather than having 3 15% tests, we now have 2 20% tests, and the final exam is now worth 40. In addition, the way that the course handles MSAFing a test has changed. It used to be that the weight for that test would be divided equally among the other 2 tests. It is now the case that the weighting for that test will be divided equally among the other test and the final exam. So, if you MSAF a test, the other test is worth 30% and your exam will be worth 50% of your final grade. So, there you go. Let's see. Mechanics. Oh! Oh, yeah! Like, statics, right. Cool. Okay. Yeah, I don't know, like, the concern that I had is, like, ordinarily, the thing I've been trying to do with the tests is, like, divide them up as equally as possible through the semester. So, I, if I couldn't have them at 4, 8, and 12, I wanted to have them at 12 and 6, but 6 is reading week, so I moved it a week later. And if we move test 2, well, I suppose that still gives us a 4-week gap between the two tests, which is what we were at before. But, alright, so November 21st, math is the 20th. Which math course? Okay. Okay. So let's do a poll. For all of you students in the class, if you think that the test situation is okay the way it is, the way that it's laid out right now in the syllabus, put I into, like, A-Y-E, I into the chat. And if you think that the test would be better if it were moved, put nay into the chat. 2Z03, that sounds like engineering calculus. Don't underestimate statics, by the way. Yeah, and I'm sorry this is eating into the lecture time again, but it's important to get this stuff right. Well, I didn't see a single negative there. And that might not be the whole class, but it seems like nobody has, it seems like everybody's okay. Yeah, it sort of seems to be the perspective. If it has to be, then it has to be. Yeah, okay. We'll keep the midterm there then. Yeah. Okay. All right. Oh. We've got one guy who says nay. I think unless you have a explicit unless, well, okay, but we can't move the entire class just to convenience one student, can we? So questions. It's open book. Yes, it's open book. It will not be multiple choice, Anthony. You will, well, it will not be exclusively multiple choice. It might be, there might be multiple choice questions in it. I probably would be more inclined towards short answer or long answer even on the October 24th and November 28th, I believe. Or, let's see. Forget it already. Jeez. Yeah, November 28th. So, multiple choice, we might have some questions, but I would be more inclined to do short answer or long answer even, given that this is a take-home test. You can expect that the majority of the marks that will be up for grabs on these evaluations will be testing your ability to code. Seems I'm having buffering issues. So, yeah. Anyway, we'll talk about the midterm a little closer to the midterm. For now, let's continue with the thing that we were talking about last time. So, last time we were talking about libraries. We were talking about the difference between static and dynamic libraries. The Coles Notes version is that a static library is required at compile time and integrated into the executable at compile time. So the compiler needs to be able to find the library. When you write a file that you are using as a library for one of your projects or one of your assignments or whatever, that will be a static library. Dynamic libraries, on the other hand, they do not, the links to the functions, they are put in at compile time, but the implementation of the function itself, the pre-compiled implementation of that function from the library, is linked to the executable at runtime rather than at compile time. This means that many programs may use a dynamic library. The dynamic library may be updated without having to recompile all of the things that use it. Whereas, if you update or change a library function that's being used in a static manner, everything that uses it must be recompiled. So that's the primary difference there. Questions? Yes, it will all be through JHub. Yep. So, there are two ways to include files: using angle braces or using quotation marks. If the file name is enclosed in quotation marks, GCC will search both the first relative directory of the current file and a pre-configured list of standard system directories. However, if it's angle braces, only the standard system directories are searched. Technically, this means that you could use quotes for everything. However, by convention, if it's a file that you've written that you're including, or something local, you use quotes, and if it's a library that's a standard library header or something that's in your system directories, generally speaking, you use angle braces by convention. So, header files. We've talked about header files a little bit, but let's drill down and define their purpose a little more in depth. This is direct quotation from the GCC documentation. Header files serve two purposes. System header files declare the interfaces to parts of the operating system. You can include them in your program to supply the definitions and declarations you need to invoke system calls and libraries. So, for example, if you consider the scanf function, the scanf function is taking characters out of the standard input buffer and feeding it into your program. This is considered a function and feature of the operating system itself. You can think of opening up file streams as also being operating system features and functions. So the system header file defines your interfaces. In other words, if we remember to function prototypes, it provides the function prototypes for all of these operating system functions. Your own header files contain declarations for interfaces between the source files of your program. Each time you have a group of related declarations and macro definitions, all or most of which are needed in several different source files, it is a good idea to create a header file for them. So, header files can do a few things. We'll get into macros. We'll discuss what a macro is and how to use it next in topic 4. There's a certain amount of definitional stuff that you can include inside of a C file other than the definitions and declarations of functions. These are the sorts of things that you would typically include in a header file. But again, the purpose is to give C the interface to the functions that you want to use that may be located elsewhere. By convention, header files have the .h file extension. Although it's .h, header files are still C code. They are C encoded. Questions? What is the difference between relative directory and the standard system directories? Good question! That's a very good question. So, imagine, Python again. Imagine you have a bash prompt like this. When you have a bash prompt, you are working inside of one directory on your computer. In fact, if you open up like a file, like a folder in, an Explorer-like environment, in Linux you can open up a terminal direct there, and you can see all of the files that are in that directory. This is known as your working directory. So when I'm talking about first relative directory right here, I'm talking about the working directory that your program is being compiled in. So in this case, it would see all of the files that are inside of this directory, and it would not see any files outside of the directory if the only thing that it's looking for is stuff in the first relative directory, or the working directory. Whereas the system files in Linux, those are stored in interesting places. If you go all the way up to like the top of your operating system, you've got a bunch of these interesting folders that you aren't allowed to actually do anything with unless you invoke super user privileges, which is a thing you'll learn about in your tutorials. But if you can look in them. So if you take a look inside of sys, which stands for system, you can see we've got all kinds of interesting things in here, like devices, firmware, kernel. So if you want to take a look inside the kernel, you can see there are all these interesting folders, right? In these, there are a certain number of these directories where the operating system knows to look for libraries. Actually, it might be even in lib. Yeah. CPP? That's not a directory. Huh. Anyway, so there are a certain number of these directories that are predefined by your system, regardless of whether it's Linux or whether it's Windows or whether it's Mac. It knows to look for libraries in these places, and those are the places it looks for them. So hopefully that's an answer to your question. Can you link a header file to a header file? Yeah, sure, why not? As with a lot of things, you can, but it's not necessarily a good idea. However, you might be able to think of a way in which it's a good idea, in which case, go for it. So let's talk about what some of your standard libraries are in C. Up to this point, we haven't actually had a listing of the types of libraries that are available to you. So assert.h contains information for adding diagnostics that add in programming debugging. In particular, you can add assert statements, which basically allow you to crap out on errors whenever you want. C-type contains function prototypes for functions that test characters for certain properties, and function prototypes for functions that can be used to convert lowercase letters to uppercase letters, vice versa. So C-type contains character operations. Errno.h defines macros that are useful for reporting error conditions. Float.h contains floating point size limits of the system. So if you need to know more information about the floating point numbers that you're using, although floats are supported by default, they're a keyword in C, You can find more information there. Limits contains the integral size limits of the system. Local e.h contains function prototypes and other information that enables a program to be modified for the current locale in which it's running. The notion of locale enables the computer system to handle different conventions for expressing data, such as dates, times, currency amounts, and large numbers throughout the world. So that allows you to read from the computer that your code is executing on, like what your time zone is and stuff like that. Math.h contains a bunch of math stuff like cosines and square roots and all kinds of good stuff, and pow, whether or not that works. Setjump.h contains function prototypes for functions that allow bypassing of the usual function call and return sequence. You probably won't have much use for that in this course. Signal.h contains function prototypes and macros to handle various conditions that may arise during program execution. So that sounds like that's error handling. Standard arg defines macros for dealing with lists of arguments to a function whose number and types are unknown. Sounds like that might be useful. Standard def contains common type definitions used by C for performing calculations. stdio is obviously the standard I/O library. Standard lib contains function prototypes for conversions of numbers to text, text to numbers, memory allocation, all kinds of stuff. That's like your miscellaneous category. String.h contains string processing functions, and time.h is for manipulating date and time, as you might expect. A lot of these just do what they say on the tin. Ooh, I hate it when I click the toolbar. Ugh. There. Alright, so let's talk about example. Here is a library example. We've got 3 files here, one of which only has 1 line in it. So we got top.c. We are invoking the function max. Max is contained. The implementation of it is contained in mylib.c, and the interface to it is contained in mylib.h. Notice we are including mylib.h, but mylib.h does not include mylib.c. Yes, note that lib.c does not contain a main function. So when you're writing a library file, it's not like your library needs a starting point for execution. It doesn't need a main function. So you shouldn't include one if it's a library. So if you have a bunch of C files, only the top level C file that invokes everything else needs to have a main function. It needs to know where to start, but everything else can figure out whether it's executing or not based on that invocation, that one invocation of main. Questions? Good. Is that scroll? No? Okay. I'm going to pop out that and see if there's... Sometimes this lags behind a little bit. Nope. Okay, good. Boop, boop, boop. Cool. So, all 3 of these files are linked and compiled with a single invocation of GCC. GCC wall top.c mylib.c out top. And you'll notice that while mylib.c is not included anywhere, it is still passed into the compiler. This way the compiler knows that that provides the compiler with the definitions of the functions that are being called. If you don't want to do things that way, oh, that's the next slide, pardon me. Running GCC on top.c only, omitting mylib.c, will result in an undefined error. The max function will have no definition anywhere. And that is an actual error, not just a warning. It is a stylistic recommendation to write header files for your C files below the top level, especially if those files are large. This emulates the way that other programming languages use packages and modules. You may have heard the term API, Application Programming Interface. People, generally speaking, like using APIs because it saves them the work of implementing things themselves. Some people think that programming is primarily a matter of doing the correct API invocations at the correct time and in the correct order. Yeah, looking at you, C# developers. But, you know, anyway, the header file may be successfully omitted, and you can still get things to compile correctly. If you change mylib.h to mylib.c, that invokes the mylib.c directly. And when you include a C source file directly, or when you do any of these types of include statements, the correct way to think about it is that this statement gets replaced with the body of the file. So you can think of like that portion of the file being inserted directly into your C file, and that's correct. So, like for example, any global variables that are declared inside of mylib.c become available in top.c, which is, a thing that we'll be talking about reasonably quickly. So it's like having the declaration without having the function prototype. But prototypes are good. You should practice using prototypes. Cool. So if you do that, if you change mylib.h to mylib.c, then you are now able to omit mylib.c from the invocation of GCC. Because the precompiler will go after the included file and plunk that into your file, it's no longer necessary for GCC to have that file, read into it as well, because mylib will be mylib will be placed inside of top.c by the precompiler, so you don't have to pass it to GCC. Burp, burp. Questions? Yeah. Wall is for warnings. It's WALL. It displays all warnings. Some warnings are hidden by default. So all you need to put in a library file are a bunch of useful function definitions that can be used later on. Yes, that's essentially what a library is. Why don't we put the function definition in the header file instead of putting it in a separate C file? Because you're setting up this is showing you how to set things up so that you can use your library as a dynamic library. If you follow the alternative procedure here and just include the C file directly, that makes it a static library. Whereas if you use the header file here, then essentially if you take mylib.c and you compile it separately, and this is actually what the next slide is going to be about, but if you compile it separately and put it in one of your system directories, one of these system directories that we were referring to, then that sets it up as a dynamic library. So you can, you have all of the advantages available to you from having it be dynamic. Yes. Hopefully that answers the next two questions. How is mylib.h connected to mylib.c? It isn't. The mylib.h because there's no include statement. If there was an include statement, then you might as well just put the function prototype and the implementation in the same file, right? There'd be no difference there. The point is that the interface can be defined and given to top.c without this being included necessarily. When GCC is linking things up, it's going to look around for a definition of max, right? Since max is not defined in any of the included, it's not defined in any of the included system directory, included in any of the standard libraries that we've invoked, then, you know, it's not going to find the definition unless you've passed mylib.c into GCC as well. Yeah. Hopefully those are answers to your questions. So let's talk about how to do dynamic libraries. And this, I'm not going to go into, like, there's no example attached to this for reasons that will become clear. But this is how you would make a dynamic library. For one thing, the procedure for doing so is operating system dependent. So in Windows, you have one procedure. In Linux, you have another procedure. In Mac, you have a different procedure. But in general, the goal is to create a shared library. In Mac and Linux, this is called a shared object file, or .so file. And in Windows, this is a dynamically linked library, or DLL file. You perform a special compilation procedure on the file to generate either a .so or a .dll, and then you put that file somewhere your specific operating system will find it. If you're interested in doing this sort of thing, there are lots of tutorials online about how you might go about creating a DLL and putting it in the correct place so that any program would be able to find it. If you set up a dynamic library correctly, it can be used by programs written in languages other than C, which is kind of interesting and cool. This is sort of because it's compiled, right? However, this is a big warning. Messing around in your operating system's hidden folders can have serious consequences, particularly if you start deleting stuff willy-nilly. Like there's that one episode of Adventure Time where BMO goes into BMO's, hidden folders and starts deleting things for fun, and then has to be, rebooted or whatever. That's like you can seriously damage your computer system by messing around in hidden folders. So don't do it unless you have everything backed up and you're okay with that. Don't say I didn't warn you. But yeah, that's have to say that. Yeah, cool. So that all being the case, now that we've talked about libraries, have you ever wondered how your computer keeps track of all those function calls? Well, you're about to learn for certain. Function calls are stored in your system's function call stack, or call stack, or, reverently, the stack. The call stack is a segment of your computer's memory that has been dedicated to keeping track of what functions have been called and in what order. The call stack has a fixed or static size, so you only have so much space in your call stack for function calls. If too many items are added to the call stack, this can result in an error called stack overflow. Stack Overflow is what the popular coding website Stack Overflow references when it calls itself Stack Overflow. In order to understand the call stack, we need to know some rudimentary data structures. Most particularly, we need to know what a stack actually is. So, a stack is a data structure that always returns the most recently added element. This is also known as an LIFO buffer, last in, first out. There are two primary operations on stacks. You can push an element onto the stack, and you can pop an element off of the stack. The element that is popped off of the stack is always the element that was added to it most recently. So the kitchen metaphor for a stack is a stack of plates. How you use dishes in your cupboard is how a stack works. If you have a dish that you put onto the stack, you push that, in programming terminology, you're pushing a plate onto your stack of plates, and if you want 3 plates, you take 3 plates off of the top of your stack of dishes. You pop 3 plates. Typically, undo or redo actions in many programs are also stored in a stack that has, a finite number of elements that it can hold. But rather than prevent you from pushing more actions onto it, it deletes things off the bottom of the stack. Cool. Questions? Never delete system32. Never delete system32. Ever, ever. I must counter that knowledge. So, this is a visualization of how a stack works. So if we have a stack that contains one item, which is 1, and we push 2 onto it, we now have a stack containing 2 items, 2 and 1. We keep pushing our numbers onto it, we have eventually a stack that has 6 items. There's sort of another one that's implicit in this. And if we pop these values off of the stack, we get them back in the order that they were put on. Yeah. Good. So let's talk about how this relates to the call stack. The call stack, basically, if we go back to this diagram, if you replace these numbers with various a packet of information about a function call, then you're beginning to understand what the call stack is and does. The call stack enables programs to step into functions while keeping their place in the program that called the function. So, for this and for many other purposes, it's correct to think about a function as a sub-program. So, with respect to the call stack, there's really not a whole lot of distinction that is drawn between the sort of main function of your C program and any function that main calls. In fact, the giveaway is that we call main a function. But if you think about in the previous example, max, for example, if you think about this as a sub-program, that's the correct way to think about it. So the call stack supports the creation, maintenance, and destruction of each function's local variables. So local variables will be stored in the call stack. When a function is invoked, that function is pushed onto the call stack. When that function terminates, when it finishes, when it returns a value, the function is popped from the stack. All of the local variables are contained inside of that stack frame. Those are called stack frames. And when the local variable, when the stack frame is popped, it's also deleted, and everything it contains is also deleted. That's why local variables are local. They are local to the function, because when the function terminates and is finished and is popped, the local variables go with it. Local variables are like the Egyptian pharaohs' organs. They have to be put in jars and interred with the pharaoh. I'm not sure why I thought that would be a better metaphor. So anyway, the other thing that the stack frame keeps track of is the return addresses that each function needs to return control to the invoking function. So when a function invokes another function, where you are in the program, of course, needs to be kept track of, and the return value that's given from the function that you're invoking needs to be put in the correct place in the expression that contained the function call. And all of that bookkeeping is performed by the call stack and the stack frames. Yeah, I already said that. So let's see if people aren't completely confused. Nope, people seem to be okay so far. Good. So, here's a cooking metaphor. Let's imagine that we are baking a pie with recipe cards, and the recipe card for the pie references 3 other recipes in the same card box. A card box could be thought of as the set of all of your invoked libraries, with each card being a function. Let's imagine our pie takes 3, let's call them complex ingredients: flaky pastry dough, lemon custard, and simple meringue. The algorithm for completing the task would be as follows. And this is strange because it's like the algorithm for managing algorithms. Things are getting very meta on us all of a sudden. So you proceed in the recipe for pie until a complex ingredient is called for. You take the recipe card for the corresponding complex ingredient, place that on top of the card which uses it. You follow the new recipe. If another recipe is required, then you put that recipe's card on top, and then you do that one until you either find something else that you need to. Oh my gosh, there's a woodpecker. That's so cool. Sorry. You continue whatever card you're on, you continue until it calls for something else, or you're finished with it. If you're finished with it, you remove that card from the stack of recipe cards and put it back in the box. And then you resume the recipe underneath where you left off. And that's how the call stack works, more or less. If it were a kitchen. So here's an example. We've got main invoking a function square. Square just computes the square of whatever it's given, and we just say, a squared is whatever the result of square is. Relatively simple. So, in the operating system, we invoke function main. When we have invoked function main is put on the call stack. It's automatic variable. Automatic variables that's a term that automatic means local, basically. Its automatic variables are stored inside of the context of the stack frame. This is the stack frame for main. If it's the return location R1 in the operating system, then that's also stored in the stack frame. Then, when we hit square in main, that's a function invocation. So main is a new stack frame for square is created, and its automatic variables are included in it as well. The return location is assigned inside of main. So it says, okay, this is going to be the return location. We'll put that in the stack frame as well. We then proceed to execute square until such time as we hit a return statement. And of course, in square, we're going to hit one relatively quickly. At that point, wherever R2 was, the value that is returned from square gets put there, and that stack frame is removed from the stack. It is popped off of the stack. People seem to be getting this pretty well. Good. So that's how the call stack works. You will probably hear me making reference to the call stack a few times, particularly when we talk about recursion, because recursion causes problems for the call stack in a specific manner that we will get into when we talk about recursion, which will probably be tomorrow. So let's talk about variables. When you're passing information into a function, there are, in general, two styles that are used sort of generally across programming languages. You have pass by reference and pass by value. In pass by reference, essentially what you're passing in is not the value of the variable itself. What you are passing in is the reference to the memory. So you can think of it as passing pointers around exclusively. Again, we haven't talked about pointers yet, but I hope you guys are accumulating some idea of what a pointer is from all of the times I've been talking about what a pointer is, or how they're used. So, the variables are passed into the functions as references to data rather than the data itself. Modifying the function argument inside of the function will modify the variable passed into the function within the context of the calling program. So, if you pass some if you provide some argument x to a function call, if you modify that argument within the context of the function, any modifications will show up in the invoking function or the invoking program. If you're passing by value, the types of languages that use pass by reference are Perl, Visual Basic, and Fortran, as well as a bunch of others. Pass by value is used by C, Java, and Python with an asterisk. Python loves to be a special little guy, so Python does things a little bit differently. So C technically I think should have an asterisk as well, because, well, no, it shouldn't, because if you pass a pointer in as a function argument in C, you are passing the value of the pointer, right? So, it's still passed by value. I don't know, some of this gets into semantics, but and I mean semantics in the dismissive sense, in terms of, splitting hairs on details that may not be significant. Anyway, I'll just finish the slide and then we'll be done for today. In pass by value, the bit values of the variables are passed into the functions rather than references to the memory contained in them. So modifying an argument does not affect anything outside the function's local context. C can pass by reference using pointers, but you have to do the legwork yourself. So, yeah. I'm going to see if I have any questions. So, there we go. That will be our lecture for this Thursday, the 24th of September, 2020. If you have any questions, I'll be happy to answer them now. Otherwise, we can continue this at well, tomorrow, in fact. Cool. So, that's an interesting question. If you had multiple definitions to that function prototype, would it cause an error? I believe it would be a warning, not an error, but we can test that. Let's just, there we go. We can have max defined twice inside of mylib. GCC, show all warnings, top.c, mylib. Oh, I should cat that to see. Oh, no, this one. It's importing with mylib.h. Okay, so GCC, w all, top.c, mylib.c, out top. And this is an error, actually. Yeah, so redefinition is an error. If you took this, for example, and put it into or top.c, I'm pretty sure that you would get a similar error. Yep. Or wait, does that? Let me see, did that actually save? Save, there we go. Yep, that's an error. Multiple definitions of max. So yeah, if you define things multiply, then GCC is pretty good at finding it and telling you you're dumb. So there you go. Good. So, looks like there are no other questions, so I think we'll end the stream here. Thank you very much for your time and attention, folks. Talk to you soon.